Problem number 4, we want to change from radians to degrees. We haven't done this in a while. We have the little technique where we multiply by 180 degrees over pi radians. I'm essentially wanting the radians units to cancel, so to speak. Here the pi's would divide out. 12 goes into 180 15 times, and then I would just have to reach for the calculator and figure out 7 times 15. And that turns out to be 105 degrees. Basically the same thing here in part B. Multiply by that 180 over pi. This time, again, the pi's cancel. Again, 12 goes into 180 15 times. And when you multiply negative 17 times 15, you end up with negative 255 degrees. Problem number 5. Some of the equations below are impossible equations. We want to cross those out and circle the ones that are good equations. What would make one of these impossible? Remember, it's all about the restrictions on the inverse sine functions. They're very limited. They only know about certain angles. Let's do these two first with sine inverse. Remember, sine inverse only knows about angles between negative 90 degrees and positive 90 degrees. In other words, between negative pi over 2 and pi over 2. It's never heard of any other angle. 5 pi over 6, that's in the second quadrant. It's never heard of that angle. This is an impossible equation. How about negative pi over 3 here in part D? That's fine. That's negative 60 degrees. That would be inside that zone. So this is a good equation. Okay, parts B, C, and E involve the cosine inverse function. Cosine inverse has a different restriction. It only knows about angles between 0 and pi. In other words, 0 degrees to 180 degrees. So let's see, pi over 4, that's great. That's in that zone. 5 pi over 4, that's in the third quadrant, so that's out. Negative pi over 6, that's in the fourth quadrant. Cosine inverse does not know anything about negative angles. So the only two equations that are valid are parts B and D. And now in number 6, we want to go ahead and find the solution. What value of x makes this particular equation true? This is not difficult. What am I looking for? An angle or a ratio? Well, cosine inverse takes ratios and sends out angles. Well, I already know what the angle is. I'm just looking for what ratio, what cosine ratio goes with that angle. Well, we've drawn this picture many times. It's just the 45, 45, 90. Obviously, the cosine ratio there is 1 over root 2. Or if I rationalize, it's going to be root 2 over 2. That's the ratio I would plug into the inverse function, which would then lead me to the angle of pi over 4. Part D will be similar. A quick picture will give us the answer. I'm drawing negative pi over 3. That's negative 60 degrees. Obviously, it's a 30, 60, 90 triangle. I've got the 1 and the root 3, which would be negative, and the 2. I'm looking for the sine ratio. Sine is opposite over hypotenuse, so negative root 3 over 2. If you take the inverse sine of this ratio, negative root 3 over 2, you get the angle negative pi over 3. And then number 7 is a bit of algebra review. How do you rationalize the denominator when there are two terms? Well, there's a trick. It's called multiply by the conjugate. Conjugate just means change the sign in the middle. So the trick here is, if you want to get rid of that square root on the bottom, multiply the bottom that you have now by its conjugate. So change the sign. That would be 1 minus root 3. Of course, if you do that on the bottom, you have to do that on the top as well. These problems can end up kind of messy here. What I've ended up with is a couple of FOIL problems. So I've got on the top 1 times 1 is 1. The outer would be minus root 3. The inner plus root 2. The last minus root 6. None of those are like terms, so I can't combine them at all. And then on the bottom works out a little nicer because it's the a plus b, a minus b pattern. In fact, that's why this trick works. Because the inner and outer parts with the radicals, they wipe each other out. You have a plus root 3 and a minus root 3. Those are gone. All you're really going to have is the first, 1 times 1 is 1, And the last, root 3 times root 3, is 3. There's not much I can do here to clean it up. The top doesn't factor. There are no like terms. I just have to keep writing it down. The bottom ends up being negative 2. It is more customary to take that negative and put it in the front of the fraction. And so here would be the final answer. Let's try part B. Obviously, the conjugate is going to be 3 plus root 5, top and bottom. That creates for me these two FOIL problems. The top, let's see, I have 3 times 3 is 9. The inner and outer are going to be the same. I have a 3 root 5 plus another 3 root 5 is going to make 6 root 5 in all. And root 5 times root 5 is 5. The bottom, I'll have that a plus b, a minus b thing. So 3 times 3 is 9. The inner and outer wipe each other out. And then the last is minus 5. So here's what I have now. I have 14, 9 plus 5. I have 6 root 5. And I have 4 on the bottom. This is not simplified because when I look at the three coefficients, I have the 14, the 6, and the 4. Forget about the 5. It's trapped inside the radical. But when I look at the other three numbers, I see that I have a common factor of 2 that needs to be divided out. So I'll have to divide this by 2, this by 2, and this by 2. It's all or nothing, but since I did have it everywhere, I'm required to divide that out, leading me to this final answer, 7 plus 3 root 5 all over 2. Another way I could have done that last step is I could have factored a 2 out of the top as a GCF, and then that 2 and the 4 on the bottom would have reduced to 1 over 2, and I'd end up with the same answer. Okay, part C, I have a couple of different things going on. The hint says you should probably deal with the complex fraction first. In other words, I have fractions within fractions. The simplest way to deal with that is find the LCD of the little fractions. So I have one little denominator of 2 and one little denominator of 3. The LCD would be 6. And then take that and multiply the top and bottom here by 6. Really, that means I'm multiplying 4 different pieces by 6. So 6 times 1 is 6. When I get to that fraction, 2 would go into 6 3 times, and so I'd have 3 root 3 here. On the bottom, 6 times 1 is 6, and then plus 3 would go into 6 twice, and I'd have 2 root 3 on this one. Once I have that, now I can focus on rationalizing the denominator. It's just the same trick we've been using. I'll be multiplying by the conjugate of the denominator. So 6 minus 2 root 3 would be the conjugate. Just change the sign in the middle. 6 minus 2 root 3. The top will be more involved. Let's see, I've got 36. The outer is minus 12 root 3. The inner is plus 18 root 3. And the last, let's see, it's minus 3 times 2 is 6. The 2 root 3's will make a 3, so 6 times 3 is 18. On the bottom, it is simpler. I've got the 36. The inner and the outer wipe each other out. And then minus, let's see, 2 times 2 is 4. Root 3 times root 3 is 3. So 4 times 3, that's going to make 12. Let's clean that up. On the top, 36 minus 18 is 18. Negative 12 root 3 plus 18 root 3 is 6 root 3. And 36 minus 12 is 24. And then I think I've got that same issue that happened in part B. 18, 6, and 24 all share a common factor of 6. And so I would divide that out, meaning my final answer is 3 plus square root of 3 all over 4.